Alright, hello everybody. Today we are going to be introducing the RLC circuit, the resistor inductor capacitor circuit. Normally in the series we only really talk about the mechanical ways of doing this, like doing it methodically and actually just straight up solving the question, not considering the theory too much. However, in this lesson, we are going to talk a little bit about the theory. I had to scrounge up my notes and, relook at them so that I could describe this to you because it's actually really, really beautiful math. Okay, and I know that's such a nerdy thing to say, but I think that you'll have a better appreciation for how these kinds of circuits work rather than just straight up solving them. Although we are, after this video, just going to be straight up solving these different situations of RLC circuits because I know a lot of people, like I myself, has struggled because there was not enough examples to go around. But it will be nice to have an intuitive sense as well. So, of course, we have our regular facts. We've got our DC environment facts right here. And we've got our continuity facts right here. And so, just to recap, when a capacitor is in a DC environment for a long time, it behaves as an open circuit because it can no longer be charged up anymore. So it's an infinite resistance. And for an inductor in a DC environment for a long time, it acts as a short circuit because at that point the inductor just stops fighting. Okay, that's basic E&M stuff, and we've used these rules a lot in RC and RL circuits. The continuity is the same thing. We've seen, jumps in the voltage and the current when it's vice versa. When we're finding voltage across an inductor, that does not guarantee continuity. And with an inductor, we can see jumps. With a capacitor, we can see jumps with current because of no current continuity. And so with a capacitor, right, we know that voltage is continuous, and for an inductor, we know that current is continuous. And we've got our nice little governing equations, which we're going to use. Okay, so in an RLC circuit, the question that we're trying to answer is, what is the current / voltage? But for this case, on the derivation of our second order differential equation, we're just going to consider a loop analysis situation in which we're trying to find the current. Okay, and so for this derivation, we're going to go ahead and apply a nodal analysis. Okay, so not a nodal analysis, a loop analysis. I'm already contradicting myself. So we have loop 1 right here. We're going to go through the voltage, and that's just a constant. We're going to go through the resistor, and that is, just the current times the resistance. And then the inductor is going to be Li prime. And the capacitor is going to be a pesky integral, like so. And I'm just going to put dt and some arbitrary constant. I don't really care what this is. Let's just call it k equals 0. Okay. Now, we want to solve for I, okay? So we're going to have to take the derivative of everything because of this pesky integral, okay? So we're just going to say I prime r plus Li double prime. Now we're working in our second differential equation stage, plus 1 over Ci equals 0. And if we get it into the form that we truly love and hold dear to our hearts, where the highest order derivative has 1 in it, we've got I double prime plus RL I prime plus 1 over LC I equals 0, right? And hopefully, I really, really do hope that you guys have taken differential equations just in general. But if you haven't, we are going to go over a brief overview of second order differential equations, but for the sake of this derivation, we're just going to go straight into it. So to solve a homogeneous second order differential equation, we are going to use something called the characteristic equation. I do not know how to prove it, but this is generally what you are going to remember. But we are going to essentially turn everything into a polynomial. Okay, so this is just going to be some constant, we'll just call it 1. And so now our differential equation is going to actually turn into a quadratic equation. Okay, so r squared, RL, r, and r is just an arbitrary variable that I chose. It could be s, it could be t. It's just what I used when I was taking differential equations. Plus 1 over LC, r equals 0. Okay, nope, that's actually wrong. There you go. And now we're going to go through our good old friend, the quadratic formula. And when they said this in high school, that you would have to remember it for your entire life, yes you do. So we are going to say negative RL, R over L, because if you've forgotten, which is pretty bad if you have, I'm not gonna lie, it has this form, negative b plus or minus b squared minus 4ac over 2a rooted. This is called the discriminant, and this discriminant is going to be extremely important because if you can remember from Algebra 2 days, this quadratic equation actually has 3 different scenarios, but we'll talk about that when we're finished deriving this. So we've got negative r over L, and we've got plus or minus because RL is our b, and we've got r over L squared minus 4ac, which the a is just 1, so I'm not going to even write it, and we got 1 over LC all over 2. Okay, now after doing some, let's call that r, after doing some very nice algebraic manipulations, namely taking this 4 out of here, we're going to multiply these by 4, right? Because we're gonna say this is gonna have a 4 out front, and so there's gonna be a 2 down here. So let me just show you what I'm talking about. We've got r over 2l squared minus 4, 1 over LC, and I'll show you why this matters afterwards. But we can actually take this 4 out, and we can make it a 2, and we can cancel out this 2 down here, but we're still going to maintain a 2 right here. Okay, so r in its general sense is going to be negative r over 2l plus or minus the root r over 2l squared minus 1 over LC. Okay, and we're actually going to make up some definitions. So this guy right here, not make up, like this is just the theory, like probably whoever derived this first was thinking. We're going to say, oh, this looks pretty cool and intriguing. Look, it shows up 2 times, so let's give it its own name. So we're going to call it alpha. And alpha is it basically helps with the damping. It's like, I don't remember exactly what it's called, some kind of damping constant. And basically this damping constant is just going to be r over 2l. Okay, and then you're probably thinking, if you're a mathematician and not a weird engineer or whatever, oh hey, look at this, I can put alpha in here and my equation is going to look like this. And then you're like, oh, but I hate how it looks because this is so derpy looking all by itself. It's so simplified over here. So let me go ahead and simplify this even more. And you know what I'm going to call it? I'm going to call it little baby omega O, because for some interesting reason you're going to do that. And you're going to say, I want this to be squared. So you're going to ask yourself, how am I going to make it squared? Well, I'm just going to root all of that underneath. So I'm going to say that my natural frequency, the frequency at which I expect this guy to move at, if this guy wasn't here, and this is all E&M stuff, okay? My E&M professor explained this as these two people tangoing, right? It takes two to tango. These L and C, the inductor and the capacitor, they just keep, bouncing energy back and forth, and then all of a sudden you have this resistor who's just sapping away all of their fun. It's the sweat and the tears of the people tangoing. I don't know why they're crying. They should be happy, but regardless, this resistance, their energy is fading away, and so thus we've got this alpha here. And so this is the ideal if there was no third wheel, so to speak. Okay. And so this is happiness right here. But the reality isn't happy. And so we are going to have negative alpha plus or minus the root alpha squared minus omega naught squared. Okay. So this is the general solution, solution to this characteristic equation. RC circuits are RC and RL circuits, right? We noticed that the voltage always had something of the form of, this, right? This isn't going to change, okay? So we're always going to have this nice little, thing, and this is the solution, right? So we this solution can be expressed in this form, with these constants, okay? Because and that's another proof of concept. You can just, put that in here, and you're going to see, oh, wow, it actually does work, okay? And so now comes to the second order differential equation review, like the actual review. Here, I just showed you the derivation of these nice guys, because these guys are actually going to pop up, okay? We might not explicitly mention them, but I want you to be aware of them so that you can be aware of the graphs, okay? These aren't necessarily very important in terms of solving for the actual voltage or solving for the actual current, but if you're in another class where you need an interpretation of it in a non-intro course or something like that, or you need to be intuitive about it, or if you want the graphs to actually make sense, then you're actually going to need these guys right here, because they're just special values. Okay, so I had mentioned before that we're going to need a characteristic equation for a second order differential equation. That's just how they're solved. We've got the form of x double prime, x prime, and x, and because it's second order, we're going to need two initial conditions this time. We're going to need one for the regular function, and we're going to need one for the differential equation, the first order one. And if we do have a general solution with a forcing function c right here, then we are going to have an xp. And we did talk a little bit about our homogeneous, second order differential equation here, in that it's always going to have some form of like this, right? But because it's second order, it has a little more complexity here, right? This is the complexity of that. We are going to have those three different scenarios because we have to create this characteristic equation. Characteristic equation turns a second order differential equation into a quadratic equation, and so we're going to have to solve it with the quadratic formula. And like I mentioned before, we actually have three different cases. As you know, the discriminant, which I said would come up right here, right? If this discriminant is negative, this guy right here, if it's negative, then you're going to have an imaginary number. If this discriminant is 0, then you're going to have 0 there. And if this discriminant turns out to be positive, then you're going to have a real solution. And so we actually have physical meanings for these. So the first case is the real indistinct or overdamped situation. And that's when we had simplified this quadratic equation right here into our nice little alpha and our natural frequency. We turned it into this. Yeah, we turned it into this. And so we have an overdamped situation when this guy becomes positive. Okay, so what does that mean? Well, first of all, it's going to have the form of this, and this is something you're going to have to memorize. This is something that you would have learned in differential equations. If not, if you haven't, learned that, just know that this is how it is. And it's going to produce a graph that looks something like this. So remember, the solution to one of these things is going to have, it's going to have our decaying exponential right here. It's going to look like this. Okay? So we have this decaying line right here, and it's not going to touch it. Okay, there's no oscillation, there's no ability for this capacitor and resistance to tango, so to speak. No ability for them to transfer energy towards each other because the resistor is taking it all. Okay. In case 2, they had one good little dance. Okay, they had one good little dance because these R's right here, they're equal, and they create this differential equation right here, once again, or solution, once again, to the homogeneous equation. Once again, you're going to have to memorize this, and this is called critically damped, and that's where alpha, the resistivity, not resistivity constant, the damping constant is equal to the driving frequency, the square of it. Okay, well, they're equal. And finally, the most interesting way, we have the two tangoing for a certain amount of time, and then eventually the resistor wins and it gets rid of it just becomes DC after that. Once again, we have an envelope of AE minus S over T or tau, or however you want to call it, S, R, whatever. Actually, technically should be R, because I'm using R. And we will get this form right here, e to the negative alpha t, where alpha is this alpha right here, t cosine beta t, and beta is actually equal to the driving frequency, which is equal to the omega, the natural, minus the alpha squared. Okay, and there's a derivation for this as well, but essentially this is saying that you have this driving frequency and it is going to be less than this natural frequency because there is a dampening effect. This damper is going to is going to make this driving frequency not as good as this natural frequency, and so this is going to be the form right here. Okay, that's a lot of background. I actually did have a problem set up for this video, but I just realized that I yapped too long about the theory. We're going to get straight into the mechanical side in the next video, where I'm going to actually go through a problem with each one of these situations. We're going to find either the current or the voltage or both. It depends on the problem that I make. And then after that, we're going to do some more advanced looking problems, like technically advanced, not theoretically advanced. It's going to be the same thing, but technically advanced. And then after that, we're going to be finished with this unit, and we're going to move on to the last one, which is pretty fun for an electrical engineer. All right.